Hello there, beautiful human. It's your boy Chad, your favorite ripped and rizzed up physicist. Thank you for joining me, because tonight we are living large. We are talking about the biggest thing you have never seen, the mind-meltingly massive structure we call the cosmic web. So whether you are watching from your bed, your couch after a long day, or from some other cozy corner of the planet, just settle in, get comfortable, let your mind drift, and if it feels right, drop a like and comment to let me know where you're watching from. Now let us get into it. Take a moment and picture something familiar. Think of a spider's web on a quiet morning, the way it stretches between branches, its threads glistening with dew, connecting point after point in a delicate but surprisingly strong pattern. Now take that image and expand it beyond anything you have ever imagined. Stretch it across not meters, not kilometers, but billions of light years. Replace the silk threads with rivers of invisible matter and streams of galaxies. Replace the dewdrops with galaxy clusters, each containing hundreds or even thousands of galaxies. What you are now imagining, in the broadest possible sense, is the cosmic web. The cosmic web is the largest known structure in the entire universe. It is a vast interconnected network of filaments, walls, and nodes that stretches across the observable universe, binding galaxies together in a pattern that is both breathtakingly complex and strangely familiar. Every galaxy you have ever seen in a photograph, every spiral, every elliptical, every faint smudge of light captured by our most powerful telescopes, exists somewhere within this web. Our own Milky Way is no exception. We are a single point, a single node, embedded within a filament of the cosmic web, connected to our neighbors by bridges of dark matter and gas that we cannot even see with our eyes. And yet, despite its unimaginable scale, the cosmic web went unnoticed for most of human history. It was not until the late 20th century that astronomers began to piece together the evidence that galaxies are not randomly scattered across space. They are organized. They follow a pattern. They are connected. Understanding that pattern, how it formed, what it is made of, and what it means for the future of the universe, is one of the most profound achievements of modern cosmology. So tonight, we are going to trace the story of the cosmic web from its origins in the earliest moments after the Big Bang, through the groundbreaking discoveries that revealed its existence, to the cutting-edge science that is mapping it in ever greater detail. We will explore what it is made of, how it shapes the galaxies within it, and why it matters for our understanding of the universe as a whole. Along the way, we will meet the physicists and astronomers whose work brought this hidden architecture to light, and we will discover that the universe, far from being a random scattering of stars, is a place of deep and elegant structure. Let us begin at the very beginning. To understand the cosmic web, we need to go back to a time before galaxies, before stars, before atoms themselves had fully formed. We need to go back to the Big Bang. Roughly 13.8 billion years ago, the universe as we know it began in an event of unimaginable energy and density. In the first fractions of a second, everything that would ever exist, all matter, all energy, all of space itself, was compressed into a state so hot and so dense that the laws of physics as we understand them barely apply. Then it began to expand, rapidly, violently, and in that expansion, the seeds of every structure we see today were sown. In those earliest moments, the universe was not perfectly smooth. It was almost smooth, remarkably uniform in its temperature and density, but not quite. There were tiny fluctuations, minuscule ripples in the density of matter and energy, variations so small that they amounted to only about 1 part in 100,000. Think of it like the surface of an almost perfectly still pond, where the faintest ripples disturb the water. You would barely notice them. But those ripples, those almost imperceptible variations, would turn out to be the most consequential features in the history of the universe. These fluctuations are believed to have originated during a period known as cosmic inflation, a brief but extraordinary phase in the very first moments after the Big Bang when the universe expanded exponentially, doubling in size again and again in an unimaginably short span of time. The theory of inflation was first proposed in 1980 by the American physicist Alan Guth, who was then a young postdoctoral researcher struggling with some of the deep puzzles of cosmology. Guth realized that a brief period of exponential expansion could explain why the universe appears so uniform on large scales, and why it has the geometry that we observe. But inflation did something else as well. It took quantum fluctuations, the inherent uncertainties that exist at the subatomic level, and stretched them to cosmic scales. Those quantum ripples became the density variations that would, over billions of years, grow into everything we see. After inflation ended, the universe continued to expand and cool. For the first few 100,000 years, it was a seething plasma of particles and radiation, too hot for atoms to form. Matter and light were locked together, unable to separate. But as the universe cooled to around 3,000 degrees, something remarkable happened. Electrons combined with protons and helium nuclei to form the first neutral atoms, and suddenly, light was free to travel unimpeded through space. This moment, known as recombination, occurred roughly 380,000 years after the Big Bang. The light released at that moment is still traveling through the universe today. We call it the cosmic microwave background radiation, and it is one of the most important pieces of evidence in all of cosmology. The cosmic microwave background, or CMB, was first detected in 1965 by two American radio astronomers, Arno Penzias and Robert Wilson, who were working at Bell Telephone Laboratories in New Jersey. They had been testing a large horn-shaped antenna intended for satellite communications, and they kept picking up a persistent low-level noise that they could not explain. It came from every direction in the sky, at every time of day and night. They checked their equipment. They cleaned pigeon droppings from the antenna. The noise persisted. Eventually, they learned that a group of physicists at nearby Princeton University, led by Robert Dicke, had predicted exactly this kind of radiation as a remnant of the Big Bang. Penzias and Wilson had stumbled upon the afterglow of creation itself. They would later receive the Nobel Prize in Physics for this discovery. But the truly crucial detail about the CMB, the detail that connects it to the cosmic web, is that it is not perfectly uniform. When scientists mapped its temperature with increasing precision, first with the COBE satellite in 1989, then with the WMAP satellite in 2001, and most recently with the Planck satellite in 2009, they found that the CMB contains tiny temperature variations, hot spots and cold spots, differing by only millionths of a degree. These temperature differences correspond directly to the density fluctuations in the early universe. The slightly denser regions, the ones that were just a fraction warmer, were the places where matter was beginning to clump together under the pull of gravity, and those clumps, over the next 13 billion years, would grow and grow, drawing in more matter, merging, collapsing, and ultimately forming the filaments and nodes of the cosmic web. So the cosmic web is not a recent construction. Its blueprint was drawn in the first moments of the universe, written in the faintest ripples of the cosmic microwave background. Every galaxy, every cluster, every vast empty void between them, traces its origin back to those primordial fluctuations. The structure of the universe on the largest scales was determined, in essence, before the first star ever ignited. Now that we have seen where the seeds were planted, let us explore what actually makes up the cosmic web. And this is where things become truly strange, because the cosmic web is mostly invisible. When you look up at the night sky, you see stars. If you use a telescope, you see galaxies, nebulas, clusters. All of that, all the matter that emits or reflects light, everything that we can directly observe, accounts for only about 5% of the total mass and energy in the universe. Just 5%. The rest is made of things we cannot see directly. Roughly 27% of the universe is composed of something called dark matter, and the remaining 68% is an even more mysterious substance, known as dark energy. Together, dark matter and dark energy dominate the universe, shaping its structure and governing its fate, and it is dark matter, in particular, that forms the backbone of the cosmic web. Dark matter does not emit light, it does not absorb light, it does not interact with light in any way. You cannot see it with any telescope, no matter how powerful, and yet we know it is there because of its gravitational effects. Dark matter pulls on the things around it, bending the paths of light, influencing the motions of galaxies, and shaping the large-scale structure of the universe. The story of dark matter begins in the 1930s, with a brilliant and famously abrasive Swiss-American astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a massive gathering of galaxies about 300 million light-years from Earth. He measured the speeds at which the individual galaxies within the cluster were moving, and found something deeply puzzling. They were moving far too fast. Based on the amount of visible matter in the cluster, there simply was not enough gravitational pull to hold the cluster together. The galaxies should have been flying apart, and yet there the cluster was, bound together, stable. Zwicky concluded that there must be a huge amount of unseen matter providing the additional gravity. He called it dunkle Materie, German for dark matter. For decades, Zwicky's idea was largely ignored. It was not until the 1970s that the evidence became impossible to dismiss. The American astronomer Vera Rubin, working with her colleague Kent Ford, studied the rotation curves of spiral galaxies. According to the laws of gravity, the stars at the outer edges of a spinning galaxy should orbit more slowly than the stars near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. But Rubin and Ford found the opposite. The outer stars were moving just as fast as the inner ones, sometimes even faster. The only explanation was that the galaxies were surrounded by massive halos of invisible matter, extending far beyond the visible edges of the galaxy, providing the extra gravitational pull needed to keep those outer stars in orbit. Vera Rubin's work, conducted with meticulous care and against considerable resistance from a field that was slow to accept a woman's contributions, provided some of the most compelling evidence for the existence of dark matter. She never received the Nobel Prize for her work, despite widespread agreement that she deserved one, and she passed away in 2016. But her legacy is woven into the very fabric of modern astrophysics. So what does dark matter have to do with the cosmic web? Everything. In the current scientific understanding, dark matter is the scaffolding upon which the entire cosmic web is built. Remember those tiny density fluctuations in the early universe, the ones imprinted in the cosmic microwave background? Dark matter responded to those fluctuations first. Because dark matter does not interact with light, it was not held back by the radiation that kept ordinary matter trapped in the early universe. While normal matter was still locked in a hot plasma, dark matter was already beginning to clump together, drawn by gravity into denser and denser concentrations along the lines of those primordial ripples. Over hundreds of millions of years, these clumps of dark matter grew, forming an intricate three-dimensional network of filaments and nodes. Imagine, if you will, a vast sponge stretching across the entire universe. The dense parts of the sponge, the material where the holes are not, those are the filaments of dark matter. The holes themselves are immense voids, regions of space where very little matter exists, and at the intersections where multiple filaments meet, dark matter accumulated in enormous concentrations. These became the sites where the largest structures in the universe would eventually form. Ordinary matter, the atoms and molecules that make up everything we can see and touch, followed the dark matter. Once the universe had cooled enough for atoms to exist, gravity pulled ordinary matter into the dark matter scaffolding. Gas flowed along the filaments, funneled toward the densest regions, where it accumulated, compressed, and eventually ignited into the first stars and galaxies. The galaxies, in other words, did not form randomly, and then arrange themselves into a web. The web came first. Dark matter built the framework, and the galaxies formed within it, like dew collecting on the strands of a spider's web at dawn. This picture of the universe, with dark matter forming the invisible skeleton and ordinary matter accumulating within it, is known as the cold dark matter model, or more specifically, the lambda CDM model, where lambda refers to the cosmological constant associated with dark energy. It is the standard model of cosmology, supported by an enormous body of observational evidence, and it explains with remarkable accuracy the large-scale structure of the universe that we observe. With the theoretical framework in place, the next great challenge was to actually see the cosmic web, to map it, to confirm that the universe truly is organized in this vast, interconnected pattern, and the story of how astronomers achieved this is one of patience, ingenuity, and some genuinely astonishing surveys of the sky. The first major clue came in 1986, when a team of astronomers including Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics completed a groundbreaking survey of the nearby universe. They had been painstakingly measuring the distances to thousands of galaxies, one by one, using their redshifts, the stretching of their light caused by the expansion of the universe. When they plotted these galaxies on a three-dimensional map, what they saw was stunning. The galaxies were not evenly distributed. They were not random. Instead, they formed long, thin walls and filaments, surrounding enormous empty regions. One structure in particular stood out, a vast arc of galaxies that Geller and Huchra dubbed the Great Wall. It stretched across more than 500 million light-years, a structure so large that light itself would take 500 million years to cross it. The discovery of the Great Wall was a revelation. It showed for the first time with direct observational evidence that the universe has structure on scales far larger than anyone had previously confirmed. Galaxies are not sprinkled randomly through space. They are arranged in patterns gathered along filaments and walls, with vast voids in between where almost nothing exists. Have you ever noticed how cities and towns are connected by highways and roads, with large stretches of empty countryside between them? The cosmic web is a bit like that, but on a scale that dwarfs anything on Earth. The galaxies are like the cities, concentrated at the intersections and along the routes. The filaments are like the highways, long and thin, carrying matter from one concentration to another, and the voids are like the empty plains, vast and quiet, with very little going on. The surveys continued and grew more ambitious. The 2-degree field galaxy redshift survey, completed in 2003, mapped over 200,000 galaxies. The Sloan digital sky survey, which began in 2000, eventually catalogued the positions and distances of millions of galaxies, producing the most detailed 3-dimensional maps of the universe ever created. Each new survey confirmed and refined the picture. The cosmic web was real, it was everywhere, and its structure matched the predictions of the cold dark matter model with remarkable precision. But mapping the visible galaxies was only part of the story. Remember, galaxies represent only a small fraction of the matter in the cosmic web. The dark matter filaments that form the backbone of the web are invisible, and even the ordinary matter in the web is mostly not in galaxies. A huge fraction of it exists as diffuse gas, spread thinly along the filaments, too faint and too tenuous to be easily detected. This gas, heated to temperatures of hundreds of thousands or even millions of degrees, is known as the warm-hot intergalactic medium, and for years it was one of the great missing pieces of cosmology. Scientists knew it had to be there. The total amount of ordinary matter predicted by the Big Bang model, based on the abundances of light elements like hydrogen and helium, was well established. But when astronomers added up all the matter they could see, the stars, the galaxies, the gas clouds, it did not add up. Roughly half of the expected ordinary matter was unaccounted for. It was missing. Not dark matter, which is a separate issue entirely, but ordinary matter, the same protons and neutrons that make up everything familiar. Where was it? The answer, it turned out, was hiding in the filaments. In 2018, 2 independent teams of scientists found the missing matter. Using a clever technique, they looked at pairs of galaxies that were known to be connected by filaments, and searched for faint distortions in the cosmic microwave background caused by hot gas along the line of sight. This effect, known as the Sunyaev-Zeldovich effect, after the Russian physicists Rashid Sunyaev and Yakov Zeldovich who predicted it, occurs when high-energy electrons in hot gas scatter the photons of the cosmic microwave background, slightly shifting their energy. By stacking the signals from thousands of galaxy pairs, the teams were able to detect the faint signature of gas in the filaments, confirming that the missing baryons, the missing ordinary matter, had been hiding in the cosmic web all along. This was a profound result. It meant that the cosmic web is not just a pattern traced by galaxies. It is a physical structure filled with matter, connected by real bridges of gas and dark matter. The filaments are not empty highways. They are rivers, carrying matter from one part of the universe to another, feeding the galaxies that reside within them. More recently, direct observations of the cosmic web have become possible through other methods as well. In 2014, astronomers using the Keck Observatory in Hawaii detected a filament of the cosmic web by observing the light emitted by hydrogen gas illuminated by a nearby quasar, an incredibly bright, active galactic nucleus powered by a supermassive black hole. The quasar acted like a cosmic flashlight, lighting up the surrounding gas and revealing a filament stretching over 2 million light-years. It was one of the first times a strand of the cosmic web had been directly imaged, and it provided a vivid visual confirmation of what had long been predicted by computer simulations. Speaking of simulations, they have played an essential role in our understanding of the cosmic web. Because we cannot experiment on the universe, we simulate it. The idea is conceptually simple but computationally staggering. You start with the initial conditions of the universe, the density fluctuations measured in the cosmic microwave background, and then you let the laws of physics run forward in time, calculating how gravity pulls matter together, how gas cools and collapses, how stars form and die, how black holes grow. Every particle interacts with every other particle, and the number of calculations required is astronomical in every sense of the word. The Millennium simulation, run in 2005 by the Virgo Consortium, using a supercomputer in Germany, tracked the evolution of 10 billion particles of dark matter from shortly after the Big Bang to the present day. The result was a stunning, detailed model of the cosmic web, showing filaments, voids, and clusters forming and evolving over billions of years. Watching the Millennium simulation unfold is like watching the universe grow up in fast forward. Tiny ripples become gentle undulations, which become pronounced peaks and valleys, which collapse into filaments that reach toward one another and connect, forming the vast web we see today. Later simulations, such as Illustris and its successor Illustris 10G, added ordinary matter, gas physics, star formation, and black hole feedback, producing even more realistic pictures of the cosmic web. Illustris 10G, completed in 2018, simulated a cube of universe roughly 300 million light-years on a side, including the formation and evolution of thousands of realistic galaxies within the cosmic web. The detail was extraordinary, down to the magnetic fields threading through the filaments and the jets of energy blasting from supermassive black holes at the centers of galaxies. And when these simulations are compared to the real universe as mapped by galaxy surveys, the agreement is extraordinary. The cosmic web predicted by theory and simulation matches the cosmic web we observe. Now let us look more closely at the components of the cosmic web itself, the pieces that make up this grand architecture. The cosmic web can be broken down into four main types of structure: nodes, filaments, walls, and voids. Each plays a distinct role in the organization of matter on the largest scales. The nodes are the densest regions. These are the galaxy clusters, enormous concentrations of matter where hundreds or even thousands of galaxies are bound together by gravity. Galaxy clusters are the largest gravitationally bound structures in the universe. The most massive ones contain as much matter as 1,000,000 billion suns, or roughly a quadrillion solar masses. They sit at the intersections of the cosmic web, where multiple filaments converge, and they are the endpoints of the rivers of matter that flow along the filaments. Think of them as the great cities of the universe, the places where everything comes together. Galaxy clusters are extraordinary environments. They are filled with a hot, thin gas called the intra-cluster medium, which is heated to temperatures of tens of millions of degrees by the energy released as matter falls into the cluster's gravitational well. This gas emits X-rays, which is how many clusters were first detected and studied. Scattered throughout this hot gas are the individual galaxies, their stars, their dust, their black holes, and surrounding everything, vastly outweighing the visible matter, is a massive halo of dark matter that holds the entire structure together. Some of the most famous galaxy clusters include the Coma cluster, the same one Fritz Zwicky studied in the 1930s, and the Virgo cluster, which is the nearest large cluster to our own galaxy, lying about 54 million light-years away. Our Milky Way is not itself part of the Virgo cluster, but it is being pulled toward it, slowly, drawn by the immense gravitational influence of all that concentrated matter. There are also even more massive structures known as superclusters, where several clusters are gathered together, connected by the filaments between them. The most famous of these is the Shapley supercluster, named after the American astronomer Harlow Shapley, which lies roughly 650 million light-years from Earth, and is one of the most massive concentrations of matter in the nearby universe. It acts as a kind of gravitational attractor, tugging on everything in its neighborhood, including our own galaxy, adding its pull to the broader flow of matter through the cosmic web. Clusters are also remarkable laboratories for studying physics under extreme conditions. The temperatures in the intra-cluster medium are so high that the gas emits X-rays, and space-based telescopes like the Chandra X-ray Observatory and XMM Newton have produced breathtaking images of this hot gas swirling within clusters. Some clusters show evidence of recent mergers, with shockwaves rippling through the gas, while others appear more relaxed, having settled into a kind of gravitational equilibrium. One of the most famous examples is the Bullet cluster, observed in 2006, where two clusters have recently collided. The collision separated the ordinary matter, which was slowed by the impact, from the dark matter, which passed through unimpeded. This separation was detected through gravitational lensing, and it provided one of the most direct and compelling pieces of evidence that dark matter really exists, as a separate substance from ordinary matter, not merely an artifact of our misunderstanding of gravity. The filaments are the long, thread-like structures that connect the nodes. They are the most distinctive feature of the cosmic web, stretching for hundreds of millions of light-years across space. Each filament is a concentration of dark matter and gas, typically tens of millions of light-years across, along which galaxies are strung like beads on a necklace. The filaments are not static, they are dynamic, active structures. Gas flows along them, drawn by gravity toward the nodes at their ends. Galaxies within filaments interact with each other, merging and colliding over billions of years. Matter is constantly moving through the filaments, feeding the growth of clusters, and the formation of new galaxies. Have you ever watched a river system from high above, perhaps in an aerial photograph or a satellite image? The way tributaries flow together, joining into larger and larger streams until they reach the main river or a lake. The filaments of the cosmic web work in a similar way. Gas and dark matter flow along smaller filaments into larger ones, which in turn feed into the massive nodes where galaxy clusters reside. It is a cosmic plumbing system, transporting matter across the universe. The walls, sometimes called sheets, are flattened, two-dimensional structures that sit between the filaments. They are less dense than filaments and contain fewer galaxies, but they are vast, spanning hundreds of millions of light years. Walls form the surfaces of the great voids, like the walls of enormous bubbles. The Great Wall, discovered by Geller and Huckra, was one of the first walls to be identified. Since then, even larger structures have been found. The Sloan Great Wall, discovered in 2003, stretches over 1.37 billion light-years, making it one of the largest known structures in the observable universe. And then there are the voids. The voids are the spaces between the filaments and walls, enormous regions of space that are almost entirely empty. Some voids are hundreds of millions of light-years across. The Bud-Tars void, discovered in 1981, spans roughly 330 million light-years and contains very few galaxies compared to its enormous volume. If you were placed inside a large void, you would see almost nothing. The sky would be dark, the nearest galaxies unimaginably far away. It would be one of the most isolated, lonely places in the entire universe. But voids are not completely empty. They do contain some galaxies, known as void galaxies, which tend to be smaller, bluer, and more actively forming stars than galaxies in denser environments. Studying these isolated galaxies has given scientists valuable insights into how galaxies evolve when they are removed from the influences of the cosmic web, free from the mergers, interactions, and environmental effects that shape galaxies in filaments and clusters. Together, these four components, nodes, filaments, walls, and voids, create the vast sponge-like structure of the cosmic web. If you could somehow zoom out far enough to see the entire observable universe at once, this is what you would see. Not a random scattering of galaxies, but a magnificent interconnected network, an architecture of light and darkness, matter and emptiness, stretching in every direction, as far as the eye could conceivably reach. One of the most fascinating aspects of the cosmic web is that it does not merely contain galaxies, it actively shapes them. Where a galaxy is located within the cosmic web, whether it sits in a dense cluster, along a filament, on a wall, or in the depths of a void, profoundly influences its properties, its size, its shape, its color, its star formation rate, and even its ultimate fate. Think of it this way. Imagine two people born on the same day, with the same basic potential. One grows up in a bustling city, surrounded by opportunities, competition, and constant interaction. The other grows up in a quiet rural area, with more space, but fewer influences from the outside world. Over time, they develop differently, shaped by their environments. Galaxies are similar. The cosmic web is their environment, and it molds them in fundamental ways. In dense regions of the cosmic web, particularly in galaxy clusters and the inner parts of thick filaments, galaxies tend to be larger, redder, and older. They have used up or lost much of their gas, the raw material needed to form new stars, and so their star formation has slowed or stopped entirely. These are the elliptical galaxies and the lenticular galaxies, massive and serene, their stars aging slowly in a kind of cosmic retirement. Several processes drive this transformation. One of the most important is called Ram pressure stripping. As a galaxy moves through the hot, dense gas that fills a galaxy cluster, the gas within the galaxy is pushed out, stripped away by the pressure of the surrounding medium, much like the wind stripping leaves from a tree during a storm. Without gas, the galaxy can no longer form new stars. It fades, reddening as its remaining stars age. Observations of galaxies in clusters have revealed stunning examples of this process, with long tails of gas trailing behind galaxies as they plunge through the intracluster medium, visibly being transformed by their environment. Another process is galaxy harassment, which, despite its somewhat informal name, describes a real and well-studied phenomenon. In dense environments, galaxies experience frequent high-speed encounters with their neighbors. These encounters are too fast for the galaxies to merge, but the gravitational tugging distorts their shapes, strips away their outer material, and disrupts their internal structure. Over time, repeated harassment can transform a spiral galaxy into a smaller, more compact form. And then there are mergers. When two galaxies collide and merge, the result is often a dramatic transformation. Spiral arms are destroyed, gas is compressed, triggering intense bursts of star formation. Supermassive black holes at the centers of the merging galaxies can become active, releasing enormous amounts of energy. Eventually, the merger produces a single larger galaxy, often an elliptical. These mergers are far more common in dense regions, where galaxies are closer together and more likely to interact. In filaments, galaxies experience a gentler version of these effects. They still interact with their neighbors, but the encounters are less frequent and less intense than in clusters. Studies have shown that galaxies in filaments tend to align their spin axes with the direction of the filament itself, a subtle but profound influence. The flow of gas along the filament also feeds galaxies, providing fresh material for star formation. Galaxies in filaments are often in an intermediate state, not as actively star-forming as isolated galaxies, but not as quenched as those in clusters. This connection between a galaxy's properties and its position in the cosmic web is one of the most active areas of research in modern astrophysics. Scientists have developed sophisticated methods to classify the cosmic web and determine where each galaxy sits within it. Machine learning algorithms trained on cosmological simulations can now analyze the distribution of galaxies and identify filaments, nodes, and voids with remarkable accuracy. These tools are revealing that the influence of the cosmic web extends down to surprisingly small scales, affecting not just the largest galaxies, but even relatively small dwarf galaxies in the outskirts of filaments. One particularly intriguing discovery is the existence of so-called pre-processing. Before a galaxy even reaches a cluster, it may have already been transformed by its journey through the filament. The gas in the filament, the interactions with other galaxies along the way, the tidal forces exerted by the filament itself, all of these can begin to strip a galaxy of its gas and alter its properties before it ever arrives at the dense cluster environment. By the time it joins the cluster, it may already be well on its way to becoming a red quiescent elliptical. The cosmic web, in other words, does not just passively hold galaxies, it processes them, reshaping them as they move through its structures, feeding some and starving others in a continuous dynamic cycle of cosmic evolution. There is also a deeper, more philosophical dimension to this idea. The cosmic web connects galaxies not just physically but causally. The matter that makes up one galaxy may have been part of a completely different region of space, billions of years ago, transported along filaments by gravity and the expansion of the universe. The gas that fuels new star formation in a spiral galaxy may have originated in the diffuse intergalactic medium, been funneled along a filament, and only recently arrived at its new home. In a very real sense, galaxies are not isolated islands in space. They are connected, interdependent, constantly exchanging matter and energy through the cosmic web. The universe is not a collection of separate objects. It is a single interconnected system, bound together by gravity and shaped by the same forces that have been at work since the very beginning. With all that we have learned, let us now turn to the frontiers of cosmic web research, the cutting-edge science that is pushing our understanding further than ever before. One of the most ambitious projects currently underway is the mapping of the cosmic web using gravitational lensing, the bending of light by gravity, predicted by Albert Einstein's general theory of relativity. When light from a distant galaxy passes near a concentration of mass, that mass bends the light, distorting the image of the background galaxy. By carefully measuring these distortions across large areas of the sky, astronomers can reconstruct the distribution of all matter, including the invisible dark matter between us and the distant galaxies. This technique, known as weak gravitational lensing, has become one of the most powerful tools for mapping the cosmic web. The Dark Energy Survey, which observed the sky from a telescope in Chile between 2013 and 2019, used weak lensing to create some of the most detailed dark matter maps ever produced. These maps revealed the cosmic web in stunning detail, showing its filaments and voids as traced by the dark matter that human eyes could never directly see. The results confirmed the predictions of the Lambda CDM model with impressive precision, while also hinting at some small but tantalizing tensions with theoretical expectations that scientists are still working to understand. Even more ambitious is the Vera C. Rubin Observatory, named in honor of the astronomer, whose work was so instrumental in establishing the existence of dark matter. The Rubin Observatory, located in the mountains of Chile, began its primary survey operations and is expected to image the entire visible southern sky, repeatedly over a 10-year period, cataloguing billions of galaxies and producing the most comprehensive map of the universe's structure ever attempted. Its weak lensing measurements will trace the distribution of dark matter across vast volumes of space and across cosmic time, allowing scientists to watch the cosmic web grow and evolve over billions of years. This will be an unprecedented view of the universe's architecture, and it is expected to provide critical tests of our current models. Another frontier is the study of the cosmic web at radio wavelengths. Hydrogen, the most abundant element in the universe, emits a distinctive radio signal at a wavelength of 21 centimeters. By detecting this signal from vast clouds of hydrogen gas, radio telescopes can map the distribution of ordinary matter in the cosmic web, complementing the dark matter maps produced by gravitational lensing. The Square Kilometre Array, an international radio telescope project with sites in South Africa and Australia, is being constructed to be the most sensitive radio telescope ever built. When complete, it will be capable of detecting the faint hydrogen signal from billions of light-years away, mapping the cosmic web in ordinary matter with extraordinary detail. There is also the intriguing question of what the cosmic web can tell us about the fundamental nature of dark matter and dark energy. While the Lambda CDM model has been remarkably successful, there are still deep mysteries at its core. We do not know what dark matter actually is. Despite decades of searching, no dark matter particle has ever been directly detected in a laboratory. There are many candidates, the most popular being a class of hypothetical particles known as WIMPs, or weakly interacting massive particles. But experiments designed to catch them, buried deep underground to shield them from cosmic rays, have so far come up empty. Other candidates include axions, ultralight particles that were originally proposed to solve a problem in particle physics, and sterile neutrinos, heavier versions of the ghostly neutrinos that we know exist. The structure of the cosmic web itself may hold clues to the identity of dark matter. Different types of dark matter would produce subtly different patterns in the cosmic web. If dark matter particles were lighter and faster moving, a scenario known as warm dark matter, the smallest filaments and structures would be smoothed out, erased by the motion of the particles. If dark matter interacts with itself, even weakly, the cores of dark matter halos would be less dense than predicted by the standard model. By studying the fine details of the cosmic web, the shapes and sizes of its filaments, the density profiles of its nodes, the properties of its smallest structures, scientists hope to narrow down the possibilities and perhaps identify what dark matter truly is. Dark energy presents an even deeper puzzle. We know that the expansion of the universe is accelerating, driven by some force or property of space that we have named dark energy. But we do not know what dark energy is, whether it is truly constant, as the simplest models suggest, or whether it changes over time. The growth of the cosmic web is directly affected by dark energy. In the early universe, when matter was more concentrated, gravity dominated, and the cosmic web grew rapidly, filaments thickening, clusters gaining mass. But as the universe expanded and dark energy became more dominant, the growth of the cosmic web began to slow. Eventually, dark energy will win. Filaments will thin and stretch, clusters will stop growing. The cosmic web will gradually be pulled apart by the accelerating expansion of space. Mapping how the cosmic web has grown over time, comparing its structure at different epochs, gives scientists a way to measure the effects of dark energy. If dark energy is constant, the cosmic web should have grown in a specific, predictable way. If dark energy is changing, the growth pattern will be different. This is one of the key goals of the next generation of surveys, including those from the Rubin Observatory and the Euclid Space Telescope. A European Space Agency mission launched in 2023, specifically designed to study the geometry and growth of the cosmic web in order to constrain the nature of dark energy. There is also a growing interest in what are sometimes called the cosmic web's extremes. Superclusters, the largest coherent structures in the cosmic web, are collections of multiple galaxy clusters connected by filaments. The Laniakea supercluster, identified in 2014 by a team led by the astronomer Brent Tully, is the supercluster to which our own Milky Way belongs. It spans over 500 million light-years and contains roughly 100,000 large galaxies. Mapping Laniakea and its flows of matter, the currents of galaxies drifting through space under the influence of gravity, has given us a new understanding of our place in the cosmic web. We are not at the center of Laniakea. We are in its outskirts, part of a small filament that feeds into the larger structure, but we are connected, bound by gravity to a web of matter that stretches far beyond anything we can see with the unaided eye. At the other extreme are the vast supervoids, The largest empty regions in the cosmic web, the cold spot in the cosmic microwave background, a region of the sky that is slightly cooler than average, has been proposed to be caused by a supervoid, an enormous region of lower than average density that cools the CMB photons as they pass through it. Understanding these extreme structures, both the densest and the emptiest regions of the cosmic web, is essential for testing our models and for understanding the fundamental forces that shape the universe. Before we draw toward a close, let us consider one more dimension of the cosmic web that resonates in a deeply human way: its remarkable similarity to other networks we encounter in our everyday lives. If you were to look at a detailed image of the cosmic web produced by a computer simulation or a galaxy survey and place it next to an image of the human brain's network of neurons, you might be struck by how similar they appear. The resemblance is more than superficial. In 2020, a team of researchers, including the astrophysicist Franco Varza and the neuroscientist Alberto Feletti, published a striking comparison of the two networks. They found that although the cosmic web and the neural network of the brain differ in scale by about 27 orders of magnitude, their structural properties are remarkably alike. Both consist of thin filaments connecting dense nodes. Both have a similar fraction of their total mass or energy concentrated in these filaments. Both organize information or matter in a way that balances efficiency with resilience. This is not to say that the universe is a brain, or that the brain is a miniature cosmos. The similarity is a consequence of the fact that both systems are shaped by similar mathematical principles: the physics of networks, the dynamics of growth and connection, the way complex structures emerge from simple rules applied over and over again. But there is something poetic about it. The organ with which we contemplate the universe shares a structural kinship with the universe itself. You can find similar patterns in other systems as well. The network of mycelium, the underground root-like structures of fungi that connect trees in a forest, sometimes called the wood wide web, shares the same basic architecture. The pattern of blood vessels in your body, branching and reconnecting, carrying nutrients from one part to another, mirrors the flow of gas along the filaments of the cosmic web. The internet, with its nodes and connections, its highways of data linking servers across the globe, is yet another echo of the same fundamental pattern. These parallels remind us that the cosmic web is not just an astronomical curiosity. It is an expression of something deeper, a fundamental tendency of nature to organize itself into networks, to find efficient ways to connect, to transport, and to communicate across vast distances. The laws of physics that shape the cosmic web are the same laws that govern the growth of a tree, the branching of a river, the firing of neurons in your mind. There is a unity to nature that transcends scale, and the cosmic web is perhaps the grandest expression of it. And so, as we bring this journey to a close, let us step back and consider what we have learned. We began with the Big Bang, the moment when everything started. We traced the tiny fluctuations in the infant universe, the subtle ripples in density that would, over billions of years, grow into the vast structures we see today. We explored the role of dark matter, the invisible substance that built the scaffolding of the cosmic web long before the first stars ignited. We followed the history of discovery, from Fritz Zwicky's early insights to Vera Rubin's meticulous observations, from the Great Wall of Galaxies to the detection of the missing ordinary matter hiding in the filaments. We examined the anatomy of the cosmic web, its nodes, filaments, walls, and voids, each playing a role in the organization of matter on the largest scales. We saw how the web shapes the galaxies within it, transforming them through processes like ram pressure stripping, harassment, and mergers, depending on their location within the structure. We visited the frontiers of research, the gravitational lensing surveys, the radio telescopes, the simulations, and the deep questions about dark matter and dark energy that the cosmic web may help us answer. And we marveled at the web's resemblance to other networks in nature, from the brain to the forest to the internet. What emerges from all of this is a picture of the universe that is profoundly interconnected. No galaxy is truly alone. Every spiral arm, every elliptical halo, every faint dwarf galaxy drifting in the outskirts of a void is part of a larger whole, connected by invisible threads of matter and gravity to everything else. The cosmic web is the universe's circulatory system, its nervous system, its infrastructure. It is the reason galaxies form where they do, grow the way they do, and evolve along the paths that they do. Without the cosmic web, the universe would be a featureless expanse of thinly spread matter, with no structure, no stars, no planets, and no one to wonder about it all. The cosmic web also reminds us of our own smallness and our own connection to the larger cosmos. The atoms in your body were forged in the hearts of stars. Those stars formed from gas that flowed along the filaments of the cosmic web. That gas was drawn to the filaments by the gravitational pull of dark matter, which itself was shaped by quantum fluctuations in the first fraction of a second after the Big Bang. You are, in a very real and literal sense, a product of the cosmic web. The same forces that built the largest structure in the universe are the forces that, eventually, led to you, lying here, listening to this, thinking about the universe that made you possible. As you settle deeper into whatever comfortable position you have found, let that thought linger. The universe is vast, but it is not cold or empty. It is structured, it is organized, it is connected, and you are a part of it, a tiny conscious node in an unimaginably vast web, connected to everything else by the same gravity, the same physics, the same story that has been unfolding for 13.8 billion years. The cosmic web stretches out in every direction, filament upon filament, void upon void, cluster upon cluster, reaching to the farthest edges of the observable universe and beyond. It is still growing, still evolving, still being shaped by forces we are only beginning to understand, and somewhere within it, on a small rocky planet, orbiting an ordinary star, in a quiet arm of an unremarkable galaxy, nestled within a filament of the cosmic web, you are here, listening, wondering, drifting. The universe made you, and it holds you still, cradled in the web of everything that ever was or ever will be. Let that thought carry you gently, wherever your mind wanders from here.